In a previous video, for this particular word problem, we solved for the weight of water that needs to be poured into a tube in order for this lid here to burst open. Well, just pop open a little bit. And for this video, we're going to change this, and we're going to calculate the height of the column of water in this tube. Find the height of column of water. That is needed in order to pop open this barrel top. We know what the force needs to be here from the previous video. Where is the previous video? Here we go. We know from the previous video the force required at the bottom of that column of water here needs to be this amount. So we can write that down. We know what the force is right here. And it's equal to 1.1425 newtons from the previous video. Now we need to calculate what the height of that column of water is. I'm going to redraw this here. There's the barrel. And here is the tube. And it has some height. The column of water here has some height to it. And we know what the force is down here at the bottom. That force is this one. And to calculate the force down here, or let's look at this another way. To calculate the pressures down here, we can use this equation. And there is the height that we're looking for. So if we use equation 23, change things over to pressures, we can calculate the height. We have a force, but if we use equation 22, we can change the force and calculate the pressure at the bottom using the equation 22. So let's do this first. Let's calculate what the pressure is at the bottom of that column of water right here. Find the pressure is here. Pressure at 2 is equal to force divided by area. We know the force. There's the force. And we know the area here from the previous video. We calculated the area. Area of 1, that area was this value. Putting the numbers here, force 1, 1.1425 newtons, divided by the area, which was previously calculated at 7.854 times 10 to the minus 5 meters squared. Therefore, the pressure here, as a result of the weight of the column of water above it, is equal to, putting this in our calculator, the answer is 14,546 and Newton per square meter. And this, as you know, is also a Pascal, but I'm going to leave it as newtons per square meter. So we know the pressure that's being generated here as a result of this column of water, and we want to find the height. We're going to consider gauge pressures. So pressure at 2. So we're considering only gauge pressure, such that we're not going to involve the atmospheric pressure. Here's the equation we're going to use, equation 23. Pressure at 1 plus rho GH. Since we're not going to include the atmospheric pressure drops out. Same as here, we didn't include the atmospheric pressure. We just calculated with the force over the area, so that's be the force of the weight of column of water. And pressure at 2 is this term. Is equal to rho GH, all of this for fresh water. That's the water that's been inside this column. Putting in the numbers, 14,546.72 newtons per square meter. Density of water, 1,000 kilograms per cubic meter. G is 9.8. And H is what we want to find, that height. All right, carrying on with this, a little bit of mathematics. Divide both sides by 1,000, divide both sides by 9.8. Divided by 1,000 kilograms per cubic meter. And divide by 9.8 meters per second squared. Looking at all these units, kilogram meters per second squared, this is a Newton, they cancel out. Cubic meters, and leaves us 1 meter in the denominator of the denominator, then it comes up to the numerator, giving us a height in terms of meters. Putting this in our calculator, well, let's do that. 14,546.277, divide that by 1,000, divide that by 9.8. The answer is 1.4843 meters. 4313, how may we write that again? 1.484313, and the unit is a meter. H then is approximately equal to 1.5 meters. We go to 2 sig figs, bring this one up, approximately 1.5 meters. So the column of water that needs to be put here above that barrel needs to be about 1.5 meters, which will generate enough force or pressure down here, which in turn, by using Pascal's principles, will generate a pressure up here onto the lid and then pop the lid open slightly. Enough to pop open the lid right here to overcome the friction force and a little bit of pressure being held here in order to pop this lid open. 1.5 meters of water.